Hi everyone, can we get started? Today we're going to look at an entirely new method for the quantification of L spectra. I'll be acting as the moderator. I should admit, however, that I'm not a spectroscopy specialist myself. So without further ado, I'll hand things over directly to Pavel. We're connecting to Dresden now. Hi Pavel, can you hear me?
Yeah, yeah, yeah. Hello, James. Hello, everyone. Can we start? Okay. Well, today I would like to broadcast some slides which were already presented almost 1 year ago in Microscopy and Microanalysis Conference in Salt Lake City. And the reason why we repeat it now in YouTube is that we are about to implement these features in our software, and probably users should know exactly what's going on behind the software they use. Well, also a lot of microscopists missed this event in Salt Lake City, especially European microscopists, so it would be not bad to repeat it. Well, the title is A New Approach for Quantification of Ill Spectra, and indeed there are a couple of really new things in this presentation. Well, I will try to follow exactly like it was in Salt Lake City. I didn't change anything in my slides, and I also try to use wordings as there. Good. So we start. First of all, you might wonder why we again treat this very old topic. I think maybe 50 years people are working on quantification of ill spectra, and very serious people were involved there. For instance, Gaten, for instance, Yemat in Antwerpen, or Hyperspy team. But last decade something has changed. Namely, we start to collect spectra in much larger energy region. Such large region that the old models and assumptions sometimes really fails in this extended region. And another thing, maybe even more important, we now collect spectrum images in huge size. So any user interaction like adjusting of some parameters becomes very problematic. So ideally, we need some algorithms which treat ill spectra with little or no user interaction. And that is our target. And that makes all business different. Well, of course, in this short presentation, I cannot review all details of our quantification algorithm. I will focus only on three points. First point is how to choose the energy ranges for fitting. Well, to my mind, it's more or less evident part. The second point would be much more critical. This is modeling of background, and to my mind, this is the central problem of all ills quantification business. Everything depends cruelly on how you model background. And you know, background in ills, it's a huge problem. It typically dominates over other useful signal, and if you do not model it accurately, you come to very bad results. Okay, and the third point is maybe not very critical, but also sometimes creates a lot of headaches. This is account for fine structure, which is sometimes called illness. Okay, so let's start with the first point, energy ranges. There are several approaches to that. For instance, sometimes people say we must model all available, all recorded energy ranges without any exceptions. Okay, that's great, but my question is, what if a big part of your recorded spectra is nothing but just irrelevant background? Trying to model it, trying to include that correctly in the model would probably only increase the danger of artifacts. Maybe it's better to reduce somehow the fitting ranges. Another opposite approach is just fix a fitted range for each and any elements. Okay, that is, for instance, implemented in Gatan digital micrograph when where there are fixed initial ranges. Of course, later user can slightly change it, but initial values are suggested for you. Well, to my mind, it's overly complicated to define it for each of 100 chemical elements, and each element also has a lot of ionization ages. So maybe something a bit simpler. Well, we decided for simplicity to fix fitting range, but fix it not in the normal scale, but in logarithmic scale. And in fact, it's not very far from the approach of Gatan, because if we consider their fixed energy windows for light elements, they are very small, and with increasing atomic number of elements, they become wider and wider. But if we recalculate them in logarithmic scale, we find that they are more or less constant. They change from 0.35 to maybe 0.5, and that is nearly close to fixing range in logarithmic scale. So, but important difference. In our case, our fixed range is much higher than that standard for Gatan. It's not 0.3 or 0.4, but 0.6, and that makes the typical fitting range quite large. As a consequence of that, very often we have several overlapping edges in ranges. Then we have to fit them simultaneously in parallel. Here I show you some example. This is nitrogen, titanium, and germanium, and each edge has its range. For nitrogen and titanium, they overlap, so we merge them in one so-called patch. Germanium is individual patch, and important is to mention that if there are several pages, we fit only within pages. The energy range in between pages we do not consider at all. Okay, more or less clear, I guess. To make the story a bit more complicated, I note that there is also another range, so-called pre-edge range, which is normally used to extrapolate the background from before an edge. And these ranges should be also defined, and we define them also in logarithmic scale. But in contrast to the signal ranges, when we join several edges in patch, we leave only the pre-edge region with the smallest energy. The reason why we do that would be clear a little bit later from the next slides. Okay, good. I think that's more or less clear with the first point. To my mind, that's evident. The second point would be much less evident: background correction. Well, you know that traditionally background is modeled with power law with two parameters. Just intensity and so-called exponent of power law, R. And it was successful for a long time when people typically consider relatively narrow energy regions. But when we start to increase our fitting regions, we find that exponent R is not constant. Here is an example. We consider materials which do not show any ionization edges. So all evolution of R constant is only due to background. And you see that exponent is not constant. It can either increase or decrease with energy loss. Well, this problem is not new. People realize that already for a long time and try to fight with that. The typical approach here is model background not with one power law but with several power laws. For instance, whoever used linear combination of two power laws, and Wouter van den Broek used up to 5 power law terms. Well, we decided to go completely different way. And to explain you, I will first mention that the power law dependence, if we cast it in logarithmic coordinates, both in x and y, it's just a straight line. And exponent r is nothing but inclination of this straight line in logarithmic space. Okay, then how about changing it a little bit? Deviate from straight line, replace it for some smooth curve. Well, something like that probably. Replace with a cubic polynomial, and we have to restrict cubic polynomial at the ending points. So it's probably better call it cubic spline. Well, according to our approach, this spline should be exactly same as straight line in pre-H region. But if we come to the end of the fitting region, it might deviate. So we get two new additional fitting parameters. The value of the spline at the end of the region and the exponent parameter at the end of the fitting region. Well, we call that approach smooth background, and it has several advantages. First of all, by definition, in the pre-H region where there is no ionization edges, it coincides exactly with pre-H power law. At the end, it might slightly differ. And as you will see, such model can simulate the change of exponent in power law up to quadratic variations of R. Well, so far so good, but if you try to fit within this approach, you immediately come to great problem. Your background very often would get crazy with some strange shapes, and system would still pretend that the fitting is the best. That is because simple cubic spline do not consider any physical constraints, while in fact we have to constrain them. We have to set the requirement. Background first should monotonically decrease. I'm not aware in any experimental data that ILS background can increase. And the second, it should not show any pronounced convex shoulder. It should be more or less smooth. Well, we deduce some constraints. I will not bother you with all mathematical derivations. Just mention that the task becomes much easier if we recast that in dimensionless coordinates when energy changes from 0 to 1 and intensity also change similarly. And if we also introduce some additional parameters which couple the final exponent value and final background value, then we come to quite simple formula. This is conditions for fitting parameters which guarantee that background is still monotonically decreasing and still smooth. Well, results. Sometimes our smooth background is almost same as a simple power law, but sometimes it deviates noticeably. The advantage of smooth background is especially clear when in the cases when simple power law simply intersects the spectrum somewhere. It's not very rare case, and in this case ILS quantification of course fails completely, but our smooth background still makes a good job, like shown here. Well, that was second and most important part. So let's come to the third part, account for near-edge structure, LNES. Also makes a lot of troubles in quantification. You know, even if your background modeling is perfect, still it would be deviations between experiment and theoretical calculations. And that is because calculations are from single isolated atom, but in fact we are dealing with atoms in solid state, and there are solid states which modify the scattering shape, and everything is more complicated. Fortunately, as clear from just from the name near edge structure, these deviations are pronounced only just near the onset, and if we increase energy, they decay, they disappear. Well, there are several approaches how to strike with these unpleasant effects, and the simplest one is just to exclude a certain energy region just near the edge, exclude it from the fit, and that is realized in digital micrograph when you can manually a little bit vary this exclusion region and achieve some visually the best result. As I thought, our target is completely autonomous treatment without users, so we cannot go this way. Well, another approach is somehow explicitly model these extra peaks and extra features near the edges. It implies introduction of a number of new parameters. And of course, you know, with sufficiently large number of parameters, we can model anything, an elephant. And to my mind, this approach only makes sense when we restrict somehow these extra parameters. And there are some works in that direction, but to my opinion, they are still not fully convincing. Well, how we treat this near-edge structure. Our approach is fully empirical. to clarify that, let's consider some, let's say, extreme cases of near-edge structure individually for K, L, and M edges. And I took, for instance, oxygen H for K, titanium, yttrium, zirconium for L, and lanthanum for M edges. We can notice that actually these extreme variations, they are near the onset, of course, and they all are inside a certain envelope defined by some empirically found function. Currently, we use simply Gaussian envelope. And what is important, these envelopes are very different for K, L, and M edges. For M edges, they are really extreme. Well, good. So it's just empirical observation. How we use that for fitting? Let's introduce a kind of weighting function. So we multiply both experiment and calculation on this weighting function and then make weighted fit. Well, how to derive this function? To do that, let's mention that far from the onset, we don't have L-ness variations at all. So if calculations differ from theory, it's only due to noise. Weighting function should be 1 in this region. But near the onset, all deviations are due to noise plus L-ness. Assuming they are independent, their variances should simply sum up, and we obtain simple equations for weighting functions. From that, we derive weighting function as this. Well, how it looks like. Here is just example. You remember that K, L, and M edges envelopes are very different, and that is examples of weighting functions with these envelopes. First of all, you notice that this weighting function depends on the noise, which is actually desired features, because if the spectra are noise-free, we have to model L-ness extremely carefully. But if we have a lot of noise in the spectrum, our fit is anyway not good, and in this situation it's too expensive to exclude very large region from the fit. Yeah, but actually, as you see from these numbers, the dependence on noise is not very strong. It rather depends on the order of magnitude of noise. Thus, noise we have only estimate just very approximately with the order of magnitude. Okay, so when you look at the shape of this weighting function, you might get that in somehow it's similar to get an approach, just exclusion of certain region near the onset, but with few important differences. First of all, our exclusion is not hard. There is no hard border, but rather soft. It's soft border between region to fit and region which should be ignored. And the second, even more important advantage, it allows naturally to account for splitting in L edges or in M edges, which can be also quite significant. And in get an approach, it's quite hard to take that into account. Well, good. Now examples. Actually, this correction is not very important for K edges, but it's significant for L edges and especially for M edges. Here is an example of fitting without L-ness correction. So you see that near the white lines fit overestimate the experiment, and at very large energy probably it will logically it would strongly underestimate that, but when we switch correction on, the fitting is quite reasonable. Okay, I think that was all what I wanted to share with you, and now we come to conclusions. First of all, I think that despite of 50 years working in the on the ILS quantification, the situation is still not in the nothing to improve state. Of course, some general trends are clear, but probably we should also try new ideas and new approaches, because there are still a lot of questions, and that is something which I also expect from you.
Thank you, Pavel. We have a couple of questions and comments. Actually, these questions were already raised about a year ago by listeners in Salt Lake City, but they have now been able to join us live thanks to a kind of a time machine. First, a comment from Nestor. This type of background modeling using a polynomial has been proposed before, for example by Jim Bentley.
Yes, I know. The polynomial modeling of background is not new, but in our case, I would not call it polynomial background because we apply exponent afterwards. The better definition is that it's still power law background, but with deviations, with cubic spline deviations at the end of the energy ranges. So it's a rather form of power law background.
Here's another question. Was it written in digital micrograph scripting and is it publicly available?
That was written in Python because the whole project was aimed for cells up Pantarray, and Pantarray is completely in Python. I have certain experience in digital micrograph, but I'm not sure that the algorithms can be easily transferred to Gatan scripts because few procedures might be not available or might be too slow.
Then, your fitting seems to be non-linear. Do you think it has advantages over the linear fit procedures?
That is a very good question. Indeed, non-linear fitting has several disadvantages comparing to a linear fit. And one disadvantage is that we are not guaranteed that there is only one minimum. But that is not our case. Let's look at my backup slide. We actually constrain the fitting parameters within the very narrow range. And within this narrow range, we always have only one minimum. And also you can see that the loss function is convex relative to these fitting parameters, and that means that we can employ very efficient searching algorithms which converge quite quickly. But still, of course, the fitting procedure is noticeably slower than that in linear fitting algorithms. Mainly that is because of overheads. Probably we can further optimize that by optimal compiling of whole procedure. But for the moment, it's noticeably slower than the linear fit.
Unfortunately, we have to stop here, as I need to return urgently to our headquarters. On behalf of TEM-DAYM, I would like to thank all our listeners for their attention. If you enjoyed this webinar format, please leave a comment on our website. If there is enough interest, we will probably continue this series. Thank you for joining us, and see you next time.
Thank you, James. Thanks everyone for your attention. I only want to mention that for the passing year we formulated all these algorithms in quite detailed and compressed manuscript, which you can download with the link mentioned in description of this video. Bye everyone.